Hi, in this lecture, we're going to delve into linear algebra for artificial intelligence. Artificial intelligence itself incorporates a vast amount of mathematical concepts. Not only geometry, but also linear algebra and statistics are among the various mathematical elements heavily involved. Among these, linear algebra is considered one of the key mathematical theories in artificial intelligence. Hence, without a solid understanding of linear algebra, you might find it challenging to read AI research papers or develop your own AI models, often requiring considerable effort and time. Therefore, having a basic understanding of linear algebra enables an easier and more convenient approach to AI, which is why we are conducting this linear algebra lecture for AI. Linear algebra itself is somewhat a complex field of study, and it has a long history as well. So, covering the entire field of linear algebra can be quite complex and difficult. So, we'll review the linear algebra theories commonly used in AI and see how they are applied in AI in this lecture. I've listed three keywords here: vectors and matrices, their geometrical meanings, and how they are used in AI. These three topics are not everything about linear algebra, and they don't cover the entire field of linear algebra, but they're essential elements for understanding AI. Technically, our last topic, application to AI, is about how linear algebra is used in AI, so the first two topics are more crucial when studying linear algebra. Linear algebra is a study of numbers, and although it's a study of numbers, it is primarily focused on the operations of vectors and matrices. You might not be familiar with the terms vector and matrix, but you can think of vectors and matrices as arrangements or collections of numbers. A vector, for example, is a collection of numbers arranged either vertically like this or horizontally like this, representing a series of numbers in a row or a column. Matrices, on the other hand, are two-dimensional structures formed by vectors. We'll look into the functions or meanings of vectors and matrices and how operations involving them can be applied. In linear algebra, operations are crucial, with addition and scaling being considered the most important. As a side note, we also have subtraction operation naturally followed by addition. Scaling, or scalar multiplication, is similar to multiplication, but it also includes different elements. Scaling is similar to simple multiplication we learned in elementary school, like 3 times 5 equals 15, and that's why we call it scalar multiplication. You might feel unfamiliar with the terms, but it's crucial to understand that multiplication here differs from the general concept of multiplication. So keep in mind that we have the operations of addition and subtraction, as well as scalar multiplication. It's important to note that scalar multiplication and multiplication for numbers are different, and scalar multiplication is for vectors and matrices. Now, let's explore the types of data to which addition, subtraction, and scalar multiplication can be applied, as well as how these operations can be applied to those data. Here, I've listed different types of data. Essentially, most things in our world can be considered data. Why are they data? In the case of images, they represent visual elements on a plane. But if you look at an image on screen more closely, they are composed of very small units called pixels. So, when we talk about resolution, for each pixel in the image, there are given values for colors like RGB. Therefore, an image essentially has dimensions of x and y, each representing the length and width of the image. Plus, for each pixel, there are RGB values. So, x representing the length, y representing the width, and RGB values together make an image, three-dimensional data. In the case of languages, my voice is recorded over time while I speak, and it forms time series data. What about words? Consider the word scalar. Scalar is composed of 6 letters S, C, A, L, A, R, arranged in a row, and each letter requires memory. Thus, words are data as well. Similarly, numbers like 3 or 6, dates like April 9th, and times like 12:15 are also forms of data. Therefore, it's necessary to understand the forms this data can take. There are various forms, including the ones introduced earlier, but let's discuss a few key ones. Let's talk about points first. Points are literally dots. They are data defined by a single point. Let's think about this conceptually for a moment. There's just a dot existing. In other words, it either exists or it doesn't. In the case of scalars, however, we are talking about one-dimensional data. We all know about one-dimensional data because we've learned about them in elementary school. We learned about the number line, where we place a zero at the center. And then, in the earlier years of elementary school, we learned about moving forward to 1, 2, 3, and so on. As we progress, we learned about negative numbers, realizing that the number line also extends backward. So, scalars belong to one-dimensional data, and they are the data that can be represented by some number on the number line. Vectors, on the other hand, start increasing in dimensions. They are two-dimensional data. You can think of two-dimensional data as having two number lines, like I've just drawn a horizontal number line here. You can also draw a vertical line. Let's call this vertical one y. It can also go 1, 2, or -1, -2. Now, how can we represent data here? In this case, data can be a point on the plane. This point has both x and y information. It holds two pieces of information at the same time. So, for example, if I want to represent a certain data point, and it's located here, then its x information is -2, and y information is -1, meaning this data has a value of -2 and -1. In the case of one-dimensional scalars, this data only had the x information of -2, but when it becomes a vector, dimensions increase like this. Dimensions can grow further. Although we are talking about 2 dimensions, obviously, dimensions can increase even further. Let's think about a third axis coming out of the screen, and we'll call this axis z. So there's also a value coming out of the screen, right? Let's say the new value coming off the screen is 3. So if it's -2 and -1, and it comes out 3 units from the screen, now we have 3 information. Now the data contains 3 values, -2, -1, and 3. A two-dimensional data doesn't mean that there are 2 axes, and the number of axes can grow larger. They can grow, but still, all of the information can be represented as a single line of scalars. That's why it's a vector. Vectors can be thought of as lists of scalars lined up one after another. Of course, the mathematical definition might be slightly different, but for now, if every information is listed in a single line, we'll call it a two-dimensional data. So what is a matrix then? You can think of a matrix as a two-dimensional vector. What I mean by a two-dimensional vector is that in a matrix, vectors are lined up as scalars are lined up in a vector. A tensor is a two-dimensional version of a matrix, and a higher dimensional tensor is a two-dimensional version of the tensor. Theoretically, saying a vector is two-dimensional and a scalar is one-dimensional, well, that's not exactly a mathematical definition. But, to summarize, a scalar represents numbers like 1, 3, or 5, and they are the numbers themselves. A vector has one more dimension, so it's a collection of scalars. When these vectors go up one more dimension, vectors stack up and stack up and stack up and eventually show this form, and we call it a matrix. So you can think of dimensions of data as going up one at a time. Let's see how we represent this data. For example, these scalars are numbers, and numbers like 1, 3, or even pi are scalars. So these scalars belong to the real number domain. Or if it's something like 1 plus 3i, it's a complex number, so it belongs to the complex number domain. So we can express a scalar as an element of a set, like this. A scalar can belong to real numbers, complex numbers, or integers. If it belongs to integers, we represent it with capital Z. And if it belongs to natural numbers, we represent it with capital N. Scalars belong to a certain number system. Let's think about vectors. Vectors can be thought of as a list of two scalars, like this, or it can be a list of three scalars, like this. And it can even be a list of 5 scalars. That's why I said it's not mathematically correct to say that vectors are two-dimensional, and it's more accurate to describe vectors as a data with one higher dimension than a scalar. So this one has 2 numbers, right? Since there are 2 real numbers, this vector is a collection of 2 real numbers. This one is a collection of 3, and this one is a collection of 5 real numbers. So if a vector is an element of r to the power of n, it means that inside the vector, there are n real scalars or n real numbers. That's the correct way to understand it. So the basic representation of the vector looks like this. Let's talk about matrices. As introduced, the dimension of matrix is 1 higher than of a vector. I will write the new matrix on the board. It has 3 vectors inside it, like this. Inside the matrix, we have a couple of pieces of information to consider. The matrix is composed of 3 vectors, and each vector is a vector of 4 scalars. And this is how we represent this matrix. The number of row is 3, and the number of column is 4, right? So we write the number of rows first, and then write the number of columns next. And that's the size of the matrix. So let's say we have a matrix A. If the matrix belongs to n by n matrices, what does it mean? It means that the vertical length of the matrix A is n, and the horizontal length is m, defining the size of the matrix. Now, let's shift our perspective a bit. If we have a data from n by 1 matrices, what does it mean? The vertical length of the data is n, and the horizontal length of the data is 1. Thus, it's a vector. What if our data is from 1 by n matrices? The vertical length of the data is 1, and the horizontal length of the data is n. So it's a vector as well. Even if our data both look like matrices, they are still vectors. So be careful not to be confused even when they look like matrices. Lastly, let's talk about tensors. What are tensors? They're like matrices stacked up, right? So the structure of tensors are more complicated. Let's think about an image. Say it has a resolution of 360 by 480, and each pixel has 3 RGB data, right? So the dimension of an image is multiplied by 3. In the case of tensors and higher dimensional data, you just multiply the dimensions like this. For higher dimensional tensors, we multiply additional dimensions to it. That's how we define the dimensions of tensor. So far, we defined the dimensions of scalars, vectors, matrices, and tensors. Let's summarize. A scalar is an element in real numbers. They are just real numbers, right? A vector is a list of scalars or real numbers with one higher dimension. The dimension of a matrix is higher than the dimension of a vector by 1. Lastly, tensors represent any data with higher dimensions, and it can go higher. That's why the earlier explanation of dimensions, like scalars are one-dimensional and vectors are two-dimensional, are not accurate. They were just to show that they increase in dimensions. Scalars are just a single element, while vectors have length. Matrices have length and width. And lastly, tensors have length, width, and even depth. So please remember the meanings of dimensions of these forms of data and how we can describe them.